Right, let's jump into 5.4. This is not a bad section. This is a friendly section. This is a section you want to know. Because if you're like me, I like to be lazy. Okay, maybe that's not the right word. I like to be efficient. I don't like wasting time doing nonsense when there's a quicker trick through. We all like a quick trick through something, huh? So let's talk about it. Now, here's our theorem. It's integrals of even and odd functions. And I'm not sure if you remember all your even functions and odd functions. With algebra, it's a lot simpler to see evens and odds than it is with, say, trigonometry, or you just have to know. But here it is. Integrals of even and odd functions. Let a be a positive real number. Let f be integrable on the function on the interval negative a to a. So all we're saying here is if you have a negative number to the positive number, negative number to the positive number. All right, so if it's even, if the function is even, well, plugging in bounds other than 0 are usually a pain in the ass. Sorry for my language. So it's saying we could just take 2 times the integral from 0 to a. Instead of going negative a to a and having to plug all that stuff in, we could just say 2 times. And then with an odd, oh, this is nice. If you know it's an odd function, it's going from a negative 2 to a positive 2 of that function. You're like, bruh, it's 0. So, well, that's hieroglyphs, right? Let's look at it. So let's have a discussion about even and odd functions. An even function says it doesn't matter if you plug in a negative number, you're going to get the same value as you would get with a positive value. You're going to get the same thing, right? It doesn't matter whether you take, look, I gave you an example function, y is equal to 3x squared. It doesn't matter whether you plug in negative 1 or positive 1. The answer is freaking 3. Right? That height is going to be 3, no matter what. So maybe we look at this. We're like, well, let's go from negative 1 to positive 1. Well, we're just going to get some areas, but symmetry, y'all. Oh, dude, that could make life a little bit simpler. Now, let's look at our odd function, just an example of an odd function. And we look here and we say if you plug in a negative value, it's actually the same as if you yanked the negative out, brought it to the front, and did it with just the positive value. And we can see with an example, let's do from 1 to negative 1, or negative 1 to 1. Negative 1, 1. We have whatever these heights are. This is the negative of f of 1. This is just f of 1. I know it's notation, that gets rough, so let's get back to the picture. But since they're the same values, well, we have this nice positive area that's right here. Not to scale, nothing that draws to scale, sorry about that. And then we have this negative area, and they just cancel. They just cancel out, making life so much simpler. So let's just see it in action. So let's say we're going to find the area under the curve from 3x squared dx, but we're going to go from negative 1 up to 1. So why would we want to do this when we could do something simple? So I'm just going to write it in as that x cubed. Oh, how convenient. From negative 1 up to 1. I'm like, okay, so now I got to take that and cube it and then subtract out something and cube it. And I put in my 1 and I put in my negative 1. And we got what, 1? That's going to retain its negative, isn't it? So that's plus 1. So that just equals 2. And these are pretty simple examples to where they're not so rough to do. But we could have just said that this is equal to 2 times just 0 to 1 of 3x squared dx. And again, this isn't the best example, but there are times when, oh my goodness. Oh my goodness. So now we could say it's just 2 times our x cubed evaluated from 0 to 1. That was 2 times 1 cubed minus nothing, and it still gives you 2. So for this one, if you use it or not, the even functions, that's fine. It's the odd functions. Bruh, come on, man. Let's go. Let's see this integral. Let's go to the area under the curve from negative 1 to 1 of an odd function. Do you notice the exponent's odd? Did you see that? Do you know on the even function we had an even exponent? Oh, cool. And if you treat constants as even, I'm done talking. Okay, let's go with our next cooked up problem. So if we recognize that this is odd, who cares about the number? That's just a constant. 4 times 0 is freaking 0. and we see that we have the same number, negative and positive, that we're going from, we know this answer is 0. Why would we go through and do this extra work? Isn't it nice to just be like, bang, take that. No work. That's nice. And this pops up. So I'm going to go the long way because, all right, let's go the long way. So 4x cubed, so its antiderivative is x to the 4th. All these are cooked up. So now we have something to the 4th minus something to the 4th. But since we now have an even power, those negatives and positive, you're going to get the same frickin' answer. 1 and negative 1. So this is 1 minus, and then that's going to turn positive, which is 0. Evens and odds. Evens and odd functions. So you want to get on in there. You want to play around with this. That odd function trick is great. So once again, there is our theorem. If f is even, and you're going from negative a to a of some function, it's integral. You could just do 2 times from 0 up to a, because it's even. If it's odd, it's just going to cancel out if you go from negative a to a, and you're just going to get an answer of 0 as the area underneath the curve. All right, we'll deal with the average value of a function or the mean value theorem for integrals in the next. Moving right along.